Hello everyone, this is the third video in our playlist, and in this video we're gonna derive the expression for the heat transfer rate Q in terms of the overall heat transfer coefficient U, area available for heat exchange A, and the log mean temperature difference for a co-current heat exchanger. Explain why this is valid for a counter current heat exchanger. So we're going to be talking about the heat exchangers, and here we have a diagram that represents our problem. So we have some differential area from which the heat can be exchanged from the hot stream to cold stream, and CH here represents the hot stream, and CC represents the cold stream, and they're both in the same direction. So this is going to be the inlet, and this is going to be the outlet. So, and in the bottom we have another diagram. So the first point represents the for this particular diagram, this represents the inlet because both are starting from the same side, and this, like the second point, represents the outlet. And delta T1 here represents the temperature change, like difference in temperature of hot stream and a cold stream at point 1, and delta T2 represents the temperature difference between the hot stream and a cold stream at a point 2. And differential of delta dTH here represents the change of a hot stream over the change of a temperature of a hot stream over the differential area, and dTc represents the change of a temperature of a cold stream over the differential area. So as you can notice, because of the heat being transferred from the hot stream to cold stream, the temperature of a cold stream is going to increase, and the temperature of a hot stream is going to decrease till the end. Okay. So to start our problem, we can write down the expressions for dQ. So that's going to be equal to negative m, it's the mass flow rate, times the CPH, which is going to be the heat transfer heat capacity for the hot liquid, so it's going to be like hot water, times the delta T. So for the hot, why we have negative sign here is because the temperature is going to be negative, right? Because that's going to be like the temperature is going to decrease, so negative, it's going to be positive. So because of the fact dQ is associated with the temperature that is being transferred from hot to cold stream, that's going to become the positive heat change. And dQ for the cold stream, that's going to be the mass flow rate times the heat capacity of a cold stream times the delta T. And what we can do here is we can replace like the mass flow rates times the heat capacity with the heat capacity rates. So that's going to be CH times delta T. It's going to be C cold times delta T. Okay. So here we have our two expressions for dQ for our hot stream and a cold stream. And the next thing we can do is we can talk about the delta T. So the change in temperature is, as we said, it's going to be the change in temperature of a hot stream, temperature of a hot stream minus the temperature of a cold stream, because the temperature of a cold stream is going to be lower. And if we differentiate this, it's going to be the differential of delta T is going to be equal differential temperature of a hot stream minus the differential of a temperature of a cold stream, right? And okay, here I made a slightly mistake. So for this point, we're going to be talking not the delta, but the differential of dt. Differentials of T, hot, cold, hot, cold, because we're talking about the heat change over the differential area, right? So what we can do here now is we can replace the dTh and dTc using okay, if we consider this equation, so we know that it's going to be equal to dq, right? It's equal to dq, and if we solve for dTh and dTc, and if we make that the subject of equation and replace to our this expression, we can have something is equal to minus dq over ch minus dq over c cold. And further, if we factorize negative dq, which is going to be the differential of heat transfer rate, what we can get is that's going to be 1 over ch plus, so it's just the algebra, so we're factorizing the dq, so we are left with the 1 over the heat transfer so we have 1 over the heat capacity rate of a hot stream plus 1 over the heat capacity rate of a cold stream. So here we have another equation, which is going to be the dq, it's going to be equal to heat transfer coefficient, which is going to be the u, delta T, which is going to be the delta, so the change of a temperature, like for this specific area, for at any point, times the differential area. Okay, so it is equal to dq, right? So we can replace this dq expression for dq to our expression for our d delta t, and what we're gonna have here is d delta t is equal to negative u delta t dA times the 1 over ch plus 1 over cc, right? Okay, so if we divide both sides by delta t, something we're gonna have is derivative differential of a delta t over delta t is going to be equal to negative u times differential of a. Okay, so let's rewrite it a bit. 1 over heat rate of cold stream, heat capacity rate of a cold stream, 1 plus 1 over heat capacity rate of a cold stream times the dA. So now we can integrate those differential heat change over the differential area. So we're trying to find from the point 1 to point 2, right? So we can take the integrated from 1 to 2. Oops, what I did, like, we're going to integrate it from 1 to 2. So we're going to integrate the left side respect to delta t, and we're going to integrate the right side respect to area. So what we're going to have is, so derivative of 1 over delta t is going to be the ln of delta t1 delta t2 minus delta t1 is going to be equal to negative u times, so derivative of a, that's going to be like derivative of dA, integral of dA is going to be just a, which is the area, over 1 over ch. It's going to be just constant, like the coefficient, I mean. Okay, here we have this equation. Okay, now what we can do is the ch, so like ch and cc. We know that our rate, heat transfer rate, is equal to negative ch times the like temperature of a hot stream in inlet minus the temperature of a hot stream in the outlet, because the inlet temperature is going to be greater, right? And for the cold one, it's going to be temperature of a cold stream in outlet minus the temperature of a cold stream in inlet, because it's going to have an increase in temperature. So if we are going to manipulate this equation slightly, what we can get is, so if we find 1 over CH, it's going to become temperature, change in temperature of hot stream over, like, from inlet to outlet over the rate, over the heat transfer rate. So the same thing with the cold stream. That's going to be O minus over the. Okay, now we can replace these expressions to our delta T expression like above. So what we're going to have is ln of delta T2 over delta T1 is equal to negative UA. Let me take Q outside of the equation, and what I'm going to have here inside is THI minus THO TCO minus, right? Okay, so our problem, the question is asking us to derive the expression for heat transfer rate. So it wants us to find the expression for Q, right? So we need to make the Q as a subject. But before that, let's talk about something inside of the parentheses. So before we started the equation, in this diagram, so we said that our delta T1 is the temperature difference between the temperature difference of hot stream and a cold stream in inlet, and delta T2 is the difference in a temperature of a hot stream and a cold stream in the outlet. So temperature of a hot stream in inlet minus the temperature of a cold okay, here's the plus. Temperature of a, okay, it seems like, oh yeah, let me, yeah, so this is gonna be the temperature. So temperature of a hot stream in inlet minus the temperature of a cold stream in inlet is going to be equal to delta T1, right? And the temperature change, the temperature change, yeah, so the temperature change from the hot in outlet plus, so this thing here is going to be the negative of delta T2, and because of this negative outside of the parentheses, we can change its order. So what we can have inside of the okay, let's do it step by step. So negative UA over Q is equal to natural log of delta T2 over delta T1. Okay, so let's copy it. Okay, we don't need to copy it actually. Okay, so let's now write the expression for making the Q as the subject. So the heat transfer rate as the subject of our equation. So our Q is going to be equal to, so I'm going to get the negative sign inside of the parentheses, so it's going to make the change of the, it's going to change the order. So the terms are going to change the order times, so it's going to become delta T2 minus delta T1 over natural log of delta T2 over delta T1, right? Okay, so now this is going to be our expression for our heat transfer rate, which is Q, in terms of a heat transfer coefficient, which is U times the area heat exchange, area available for the heat exchange, that's going to be A. And this, like the fraction we have, is called log mean temperature. So it's the change between the temperature over the logarithm of them divided. Okay, here we can notice that the temperatures, our equation does not depend on anything that is related to inlet and outlet, right? So it just depends on 2 points. So the temperature, difference in temperature at point 1 and point 2. So and this is for the co-current flow, right, of heat flow. So usually they never have a co-current heat exchangers, but what they have is the counter-current. And now we're going to prove that this is valid for the counter-current flow heat exchange, because so what is going to happen is, so inlet of a hot stream is going to be the outlet of a cold stream, and inlet of a cold stream is going to be outlet of a hot stream, right? So the temperature 1 is going to become the minus this, and temperature at 2 is going to become HO minus TCI. So no matter if we replace these values to our equation, back to our equation, we're still going to have the same thing, because it's just the opposite of it, right? So because if we take the negative from the numerator and take the negative from the denominator, what we're going to have is delta T1 minus delta T2 over ln of delta T1 over delta T2. So they are, because of the fact they are equal, so they both represent the log mean temperature. No matter we're going to consider the co-current flow or the counter-current heat exchangers, we're still going to get the same expression. So this is going to be the final answer for our problem, and thanks for your attention.